Hello everyone, welcome back. In this video, we'll be taking a bit of a look at theorems in ordered fields. So last video we looked at ordered fields and the importance of order we need in our number system to do our calculus on, and we just proved that even though a field obeys the 9 axioms that we showed in a previous video, it's not a must that it's ordered. So let's look at some properties of the ordered fields and prove them. So firstly, we're told to prove that if x is greater than y and y is greater than z, then x should be greater than z. So an example of this is 5 is greater than 3 and 3 is greater than 1, then 5 should also be greater than 1. Well, this seems obvious. Let's prove this. So before we prove this, I want you guys to know x greater than y can also be written as x minus y is in P. Because, okay, for example, take example of this: 5 is greater than 3. So remember from the previous video we said element is in P if it is positive. So if 5 is greater than 3, then 5 minus 3 is also in P, because 5 minus 3 is 2, which is a positive number. So 2 is in P. So thus x greater than y can also be written as x minus y is in P. If x, for example, if x was less than y, then we would write it as y minus x is in P. So we take this. So whatever direction the arrow is pointing at, we take the element on the opposite side of the arrow. So we write it as y minus x is in P. So let's cancel that out. So x greater than y can also be written as x minus y is in P, and y greater than z can be written as y minus z is in P. So remember from our previous video, the ordered fields obeys OA. That means if x and y is in P, then x plus y is also in P. So since x minus y is in P and z minus y is in P, that means x minus y plus y minus z is also in P. And minus y plus y by additive inverse will just boil down to 0, and 0 plus x is just x because of additive neutral. I'm skipping a lot of steps here. So this boils down to x minus z is in P. And remember from here, this is the same as x being greater than z, because x being greater than z is the same as you take z to this side because it's smaller than x. It's the same as writing as x minus z is in P. So I hope you guys are getting the proof of this. We're done with the proof for part 1. So let's take a look at this one. So it says x is greater than equal to y and y is greater than equal to x. So then x is equal to y. So for example of this, if 1 is greater than equal to 1 and 1 is less than equal to 1, this shows 1 is equal to 1 because we have an and right here. So x is greater than equal to y can also be written as x minus y is in P, or x equals to y, and y being greater than equal to x can be written as y minus x is in P, or y equal, or let's say x equals y, or this is the same as y equals x. So there are two possibilities here. X being greater than equal to y means either x is greater than y. In this case, this will be true, or x is equal to y. Y being greater than equal to x means either y is greater than x. In this case, this will be true, which is y minus x is in P, or x is equal to y. And why is y minus x is in P if y is greater than equal to x? So take an example as just as we did before. If 3 is greater than equal to 1, if 3 is greater than 1, then 3 minus 1, which is equal to 2, is positive, therefore it is in P. So let's do a proof by contradiction here. Suppose for contradiction, remember we're told to prove this, we're told to prove that x is equal to y. So when we're doing a proof by contradiction, we assume the opposite. So suppose for contradiction that x is not equal to y. So in this, so x is not equal to y. So this scenario is being ruled out. So we're only being left with these two cases, that x minus y is in P or y minus x is in P. So let's see how we can handle that. So since x minus y is in P and y minus x is in P, we can add both of them. So x minus y being in P and y minus x being in P means that x minus y plus y minus x should also be in P. So, but they all cancel out to give 0, and this is a contradiction. This contradicts OT because 0 can't be in P. OT says that either element x is in P, or negative x is in P, or 0 is in P. An element can't be in both. So this scenario just breaks rules 1 and 3. So this is contradicting OT. 0 can't be in P because 0 is neither a positive or negative. So this is contradicting OT. Therefore, our assumption that x, so we assume that x is not equal to y, and this assumption is false. Therefore, because something strange just happened, so therefore x is equal to y. X equal to y when x is greater than equal to y or y is greater than equal to x. Now let's take a look at one more example. Right, it says that if x is greater than y, then x plus z is greater than y plus z. Let's take a quick example of this. If 2 is greater than 1, then 2 plus 1 is greater than 1 plus 1. This says 3 is greater than 2. So let's take a look at how we can prove this. So y, so this is the same as writing x minus y is in P. And since z is greater than 0, so z is positive, so z is also in P. Right, let's take a look at how we can prove this. So we can prove this, so we need to show. So remember, it's always good to write down what we need to show, so it directs you in a particular train of thought. We need to show that x plus z minus y plus z is in P. That's what we need to show, right? How did I get that? I just took this on this side of the equation because this is the bigger of the two. We always take the smaller one to the bigger side, and it'll always still be positive. So we need to show this. So let's simplify this. X plus z minus y minus z is in P. I'm distributing the negatives. This just boils down to x minus y being in P. Right. And but this, we already have this. So this is pretty simple proof. We already have this from here, from our initial assumption. So we're done with the proof. QE. So if you notice, these proving theorems in field axioms and ordered proving theorems in ordered fields is pretty easy. and that is how it should be. I hope you guys are all feeling it that way. There's not a lot of work to do. If you can manipulate the questions that we have, it's pretty easy to prove all of them. So let's take a bit of a look at the our fourth and final one for the video. So we can write this as w minus x is in p, and we can also write this as y minus z is in p. So we know this. Remember, this is a if then statement. If then statement can also be written as can also be denoted by a one directional arrow. So we know, so in a if then statement we can always assume the first part of the statement, the first part of the statement, and we need to show the second part of the statement. So we need to show the w plus y minus x plus z is in p. So this boils down to, I'm sorry about that. So we need to show this. So let's me simplify this. This boils down to w plus y minus x minus z being in p2. This is just w minus x, I'm sorry, wait, w minus x plus y minus z being in p. So we need to manipulate this to somehow end up with this, because this is what we need to show. So let's see what we can do right here. So we can just add w minus x plus y minus z, and we are guaranteed that they'll still both be in p. Since w minus x is in p and y minus z is in p, from OA we know that if two elements are in p, then adding them won't change where they are. Adding them will still leave them in p. So w minus x plus y minus z is in p. So let me put brackets here, and we're done. This looks exactly like what we need to show, and we're done with the proof. So proving theorems in field axioms and ordered axioms are pretty easy. I hope you guys can see that right here. Well, hope you enjoyed the video. See you next time.